Okay, so then what I want to start going through is, well, vectors is sort of mathematical preliminaries, but I want to start going through some of the sort of calculus-related mathematical preliminaries. And so the things I want to go through are first, taking derivatives of vectors. And there's an important caveat here. What we're doing in this case is taking derivatives of vectors in non-rotating coordinate systems. And this is going to be our first glimpse at something that is, it's going to be a big part of the class later on. Okay, so this is your first chance to sort of see what's the deal with rotating coordinate systems. Then second is using the product rule for vectors. Then third is using the chain rule for vectors. And then the biggest one is fourth, solving ordinary differential equations I'm going to abbreviate that ODE. That's the usual abbreviation of ordinary differential equations, using one specific method, separation of variables. Okay, so anybody who's taken a differential equations class, probably not too many of you yet, but maybe a couple of you, separation of variables. So what a differential equations class is like is you learn a million different methods, and some work in some cases, other ones work in other cases. It's pretty hard to keep them all in your head, but this is kind of the simplest one. It obviously doesn't work on everything, or this is the only one you would need to know. But this works in a lot of cases, and really I would say for people who are going into mechanics type engineering, like mechanical engineering, aerospace, or a lot of parts of civil engineering that are based on sort of mechanics, this is really the one method that you will ever be expected to come up with on your own in a class without the professor like giving you a refresher on it or whatever. Okay, so this is the one that you really want to have in your back pocket. Like, this is the one you look at an ordinary differential equation and you just check, can I do it by separation of variables? And if you can't, and all you think at that point is I'm out of ideas, that's going to be fine for the rest of your schooling, really. Okay, if you're in electrical engineering, there's a different couple of approaches that are that way, but this is the one for mechanics. This product rule and chain rule, this is also, we're thinking of this in non-rotating coordinate systems, and I'm going to try to explain why that's a big deal. Okay, so the first one is taking derivatives of vectors. in non-rotating coordinate systems. We, in this class, are not going to be taking partial derivatives. We're going to be taking total derivatives, like you saw in Calc 1 and Calc 2. And our derivatives are mostly going to be with respect to time, okay? So in this class, it's mostly going to be derivatives with respect to time. And a notation that we're going to use all the time is that, like if you have, if you want to take the derivative of some variable f, some function f with respect to time, we're just going to use a shorthand notation. This is the same thing as f dot. Okay. If you're thinking of partial derivatives, which we're really not going to do in this class, but this is not the same thing as f dot. Yes?
Is it not f dash because it's vectors?
Yeah, it's true for vectors and it's true for scalars. For now, I just want you to, I'm just saying anytime you see a dot, it's a derivative with respect to time. Okay, so if you have a vector u and you're taking the derivative of u with respect to some variable, let's call it q, just some random variable, okay, this is equal to du, the x component of u with respect to q. That's the x component of the output vector. The derivative of the y component with respect to q, and the derivative of the z component with respect to q. Has everybody gone through, like, looked at this vector review enough to know what the hell I'm talking about with this notation? So this is just the notation that I'm going to use for vectors. The top one is my x component, y component, and z component. Okay. And so if you're taking derivatives with respect to time, the time derivative of a vector u is the time derivative of the x component, time derivative of the y component, time derivative of the z component. Okay, so what that means is, let's say we have a vector t squared negative t cosine t, and we want to take the time derivative of that. And actually, let me say that this is, let's imagine that this is a position vector. Given as a function of time, okay? Well, you know that if you're in a non-rotating coordinate system, an inertial coordinate system, the velocity as a function of time is the time derivative of the position. And so that's equal to the x component of the velocity vector would be 2t. The y component would be -1. And the z component would be negative sine of t. Okay, so like if this one above is the position vector of a particle as a function of time, then you know that the velocity is this. Okay, that gives the velocity vector. Any questions about that? Okay, why does this only work in non-rotating coordinate systems? I mean, this is such a simple way, you know, it's mathematically so simple to take these derivatives. Why does this only work in non-rotating coordinate systems? Well, remember that this notation we use for vectors. So say we have this vector u, and we're calling it, you know, an x component, a y component, and a z component. Okay? But this is really just notation. The actual vector that this represents is that x component times some unit vector in a direction, the direction of x. This is the notation you saw in physics 1, right? More often, right? Plus this component, the y component, times a unit vector in the direction of the y-axis, plus the z component times a unit vector in the direction of the z-axis. Okay? And so what happens when you take the derivative? So when you take the derivative, you need to use the product rule. Okay, so what happens when you take the product rule here? I'm going to take all time derivatives of this vector u. So the product rule says you take the time derivative of this ux and multiply it by I, plus ux times the time derivative of I. Are you with me on that? Plus uy dot times j, plus uy times j dot. And now we're taking the derivative of that third term. So that's uz dot times k plus uz times k dot. Yes?
Your second J is missing a dot.
Thank you. Okay, so now let's think about what this means in rotating and non-rotating coordinate systems. In a non-rotating coordinate system, let me say this becomes, no, don't say that. Okay, in a non-rotating coordinate system, I dot, j dot, and k dot are all 0. So why is that in a non-rotating coordinate system? Why would these all be 0? Well, if the coordinate system is fixed, I have it in my direction, so here it is for your direction. Losers. So here it is in your direction. If that coordinate system isn't rotating, then I always stays in that direction. J always stays in that direction. It doesn't change in time. And so if you take the time derivatives of those, you get 0. Okay? So if it's not rotating, these are 0. And that means that U dot, you can throw out all the terms with I dot, J dot, and K dot, and you just get back Ux dot times I plus Uy dot times J plus Uz dot times K. And in our notation, we can write this as Ux dot, Uy dot, Uz dot. Okay? So that's why this works for a non-rotating coordinate system. What about in a rotating coordinate system? Well, in a rotating coordinate system, those unit vectors I, J, and K are changing in time, okay? So I dot, J dot, and K dot are not equal to 0, okay? And so I can rearrange, I'm gonna rearrange this, but what you get is that this vector U dot is equal to Ux dot times I plus Uy dot times J plus Uz dot times K. I'll group those together. Plus Ux times I dot plus Uy times J dot Uz times K dot. Okay, so cool. One question. What the hell are I dot, J dot, and K dot? Okay. So this is going to cause issues for us, you know? But as long as we stay in a non-rotating coordinate system, it's nice and clean. Okay? We know what everything means. We can take the derivatives of the components. We know the directions of the coordinate axes. Okay? So make that mental distinction now. It's going to come back later. Later, we're going to figure out what I dot, J dot, and K dot are, and we're going to be able to do calculations in rotating coordinate systems. Okay. Any questions about that right now? I know that's a fast little trip through this, but yes.
I know, like, could you please scroll it up a bit so that you can picture and copy later?
It'll be in the notes later. So why don't you just grab it off D2L? Any other questions? Yes.
When you got the two different groupings added together, it looks like you could do one step and then the next step for how one is related to the other, and then how the second is.
You're exactly right. That's what we're going to do. Yep. That, still at this point doesn't deal with what this I dot, J dot, and K dot are, but that's how we're going to approach it, yeah. Okay, so the next thing, all right, so now that is taking derivatives of vectors and non-rotating coordinate systems. Now we're going on to the product rule. And again, this is in non-rotating coordinate systems. Well, the first one I'm going to give you is the one that I just sort of glossed over and did in the last example. But the thing is, when you're multiplying vectors, there are multiple ways to multiply vectors. You can multiply a scalar by a vector, or you can take the dot product of two vectors, or you can take the cross product of two vectors. Okay, so the first one is multiplying a vector by a scalar. So if we're taking the time derivative of, let's say, some scalar a times a vector u, the product rule is time derivative is the same as dot. So this is a dot times u plus a times u dot. And in this case, we don't have to worry at all about the order of operations, because whether you multiply the vector first or the scalar first, you get the same answer, okay?
Excuse me.
Yeah.
Does the dot mean derivative?
That means derivative with respect to time. That's also in the notes. Bless you. Okay, so now, what if you have two vectors multiplied using the dot product? So we're taking the time derivative of, let's say, a vector u dotted with a vector v. Well, this is equal to u dot dotted with v plus u dotted with v dot. I mean, both of these two are exactly the way, if you had to guess, your life depended on guessing, this is what you would guess, how you did it, and you'd be right, and you'd live for another day. So what about cross product of two vectors?
Matrix?
Okay, so now we're taking d dt of u cross v. This is equal to u dot crossed with v plus u crossed with v dot. Okay, so in that, you can see all of these are kind of just the way you would guess they are. But there's one thing I want to point out. If you think of, so this works as long as you think of the dot product, the product rule as derivative of the first times the second plus the second times the derivative of the first. Okay? What if you think of it like this? With scalars, it doesn't make any difference. Derivative of the first times the second plus derivative of the second times the first. There's no difference there, right? Not with scalars. But this is with a cross product, because the order of multiplication matters in cross product. Okay, this is not the same thing as U cross V plus V dot cross U. Okay, so that's super important. Does everyone see the distinction I'm making there? Anybody have any questions about that? For the other two, it would be fine to think about it that way. Like for the dot product, this is equal to U dot dotted with V plus V dot dotted with U, because order doesn't matter when you're using the dot product. That's stuff from the vector of U. And with scalars, it doesn't matter. So this is equal to A dot times U plus U dot times the scalar A. But this is the one that you have to worry about. So you're better off thinking of it as, if you just always think of the product rule as derivative of the first times the second, plus the first times the derivative of the second, then all of these will work. Okay? This is kind of a subtle point, so this is the last chance for questions right now. I can talk to you about it after class or whatever, but yes?
This will all still work out the same if we do the operation in the parentheses
Yeah.
first.
Correct.
This has to do with the way we put it on the matrix, right?
What?
This has to do with the way we put it on the matrix, right?
Like to do the actual cross product? Yes, that's right. It depends. It's yeah, it's just which one goes on top of the matrix. That's right. If you do it the same way that I was taught to do it. Really, in this class, you probably just want to do cross products in your calculator anyways, you know. Okay, so that's the product rule. And now the chain rule for vectors. And this is for non-rotating coordinate systems. And so what we're going to see is the time derivative of a function that's a vector. And that function f is a function of, make that a g, the scalar function g of time. Okay, so then this is equal to df, where that f is a vector with respect to g, times dg dt.
So this is an injective function?
What?
Is this an injective function?
I don't know. I don't remember what that means. So you can think of this as f dot. No, you can't. You can think of this as df dg times g dot. Okay, this is going to come up in dynamics most often in a very specific way. And we'll get to a bunch of problems like this in a couple weeks or whatever. So this will arise in dynamics like this. So you know from physics 1 that the acceleration vector is the time derivative of the velocity vector, right? I'll write these as functions of time. Okay, but what if you don't know? So that's easy to do if you have the velocity expressed as a function of time. Okay, then you just use the derivative rules that I gave you at the start of the class. But what if you know the velocity as a function of a position variable, not as a function of time? Okay, rather than as a function of time. So let's say, for example, our vector v is a function of x. Okay? Well, the thing you don't want to do is, so I think we're all, like always, looking for ways to save memory space in our brains, you know, and so from physics 1, I think a lot of people get sort of the bad habit of thinking of, oh, okay, right, the acceleration is the derivative of the velocity, okay? But remember, the acceleration is not the derivative of the velocity. It's the derivative of the velocity with respect to one very specific thing, time, okay? And so the acceleration is not the derivative of the velocity with respect to x. Okay, so that's super important. Don't make that mistake. Some of you will make that mistake, no matter how many times I say it, but don't be that person. Okay? So instead, what you have to do is you're thinking of, so this velocity is the velocity vector as a function of x, which in turn is a function of time. Okay? And now you can see how taking that derivative is a chain rule thing. So the acceleration as a function of time is equal to d velocity dx times dx dt okay? And what's dx dt? This is kind of the key to this being able to work. Dx dt is the x component of the velocity, which you already have, okay? Because you already, if you're taking this derivative, you're already given an expression for the x component of the velocity. So let me show you how this works. let's say that the velocity vector as a function of, it doesn't have to be x, it could be y or z too. So let's say that velocity is a function of y, and it's equal to negative 2y, positive y, negative y squared. Okay? So what this is saying is we know the velocity vector of the object as a function of its height, say. Okay, say y is vertical. And we want to calculate the acceleration vector as a function of y. So the way we're going to do this is the acceleration vector is always defined as the velocity dt. We can't do that though because we don't have anything expressed in terms of t. Okay, so instead we're going to do it as dv dy times dy dt. And this is dv dy times the y component of the velocity based on the definition of the velocity. And so now we can calculate this. dv dy is just the derivatives of each of these components. So we have negative 2, positive 1, negative 2y. And we're multiplying that by the y component of the velocity, which is y. Multiply this all together and you get negative 2y, positive y, negative 2y squared. Okay, so anytime you have the velocity expressed as a position variable, you're going to need to use the chain rule. We'll talk more about it as we start. We're still just talking about math. When we start talking about dynamics, we'll get into this more, and I'll go back over this. But this is how the chain rule is going to come up. Any questions about that? Okay. Yes?
Can I ask why Vy is equal to Y?
Say it again. Oh, why Vy? Okay, because so the definition of the velocity vector is think of this as the definition is the derivative of the position with respect to time. Okay, and so that is the derivative with respect to time of the position vector is x, y, z. And so if you take those derivatives, this is, you can think of this as dx dt, dy dt, dz dt. Okay, and this v here is x component of velocity, y component of velocity, z component of velocity. So the y component of the velocity is equal to dy dt. The x component of the velocity is equal to dx dt. Any other questions about that yet? Yes?
Well, this not directly relates to this, but are we ever touching momentum in this class?
Yeah, very, very much later on, we will use momentum.
Is momentum P?
Yeah, sometimes we'll have to use the same variables for different things, so you just have to get that from the context of the problem. Yes.
So if we had like v of z, would then it be multiplied by v of z instead of?
Yeah, exactly, exactly. So if this was a function of, if this velocity was given as a function of z, then your chain rule would say dv dz times dz dt, and dz dt is your z component of the velocity. Exactly. Any other questions on this right now? Like I said, we'll talk about this a lot more before you need to do it, but this is just how chain rule is going to come up in this class. Okay, it's going to come up when you have a velocity function, but you don't have it as a function of time. You have it as a function of a position variable. Oh. My computer does this about once a lecture. I like it. It gives us a break. Okay, so the last part of the calculus-based mathematical preliminaries, and this is the biggest one of the 1, 2, 3, 4, is solving ordinary differential equations using separation of variables. And in my experience, if you ever in a future mechanics type engineering class see a differential equation on a test or an assignment, and you haven't talked about differential equations specifically in that class, then this is going to be the approach that you have to use. This is the only one you're going to be held responsible for as you move on, kind of. Okay. So what does it mean to solve a differential equation, an ordinary differential equation? It means to find the dependent variable as a function of the independent variable. So for example, if you have the differential equation d squared y dt squared plus 10 dy oh, forget all that. Geez, I made that look brutal. Plus 10 times dy dt is equal to 10y squared. Okay, what? Yeah. So how do you identify what are the dependent and independent variables? With ordinary differential equations, all your derivatives are total derivatives. You don't have any partial derivatives. So that's good. That makes it way simpler. Your independent variables are just what you're taking derivatives with respect to, okay? So it's what you're taking your derivatives with respect to. So in this case, you're taking derivatives with respect to t. So in this example, The independent variable is t. Is that the only independent variable? Well, here's the thing with ODEs. In ODEs, ordinary differential equations, there's always only one independent variable. Okay, in partial differential equations, there's more than one independent variable. Okay, so once you've identified the independent variable, whatever's left is the dependent variable. You can have multiple dependent variables, and we'll see that as we go. So whatever variable or variables is left is the dependent variable. So in the ordinary differential equation above, solving it means finding, what did I say, y? Means finding y as a function of time. You know, it could be 40 cosine t or something, you know. You're finding what that function is. That's what solving that differential equation means. If you have more than one dependent variable, say you have, like in dynamics, it sort of makes sense that you have differential equations that add x of t, y of t, and z of t, and you'd want to find those three functions. But since it's an ordinary differential equation, there's only the one independent variable, time. Okay, so let me get this in your notes. So in an ordinary differential equation, there's only one independent variable. This is what we're going to see in this class, ordinary differential equations. And pretty much exclusively in this class, I can't think of any cases where we'd have anything else. The one independent variable is going to be time. So we're always finding something as a function of time. Okay. Partial differential equations. So we're not going to see any of these in this class. In mechanics, partial differential equations come up in advanced mechanics of materials, when you're calculating the deformations of complicated shapes under load, and it comes up in fluid dynamics, but it's not going to come up in this case. And that's defined by more than one independent variable. And you can recognize, like, how can you recognize this? The easiest way to recognize it is that the derivatives that show up in that differential equation are partial derivatives. So like, for example, d squiggly df squiggly dx, partial of f with respect to x. Okay, all r's are going to be total derivatives. Have you ever noticed that if a movie wants to show, without explaining it, that somebody's a genius, they show them writing partial derivatives on a window with a marker? It's like shorthand for genius in movies. So if you ever want to make people think you're really smart, I mean, that's like, they'll totally fall for it. Just write symbols like this on the window.
Or maybe just go to the business class and write differential equations in the board.
Yep. Any other questions? Okay. Okay, so what's the idea of, so we'll get into this on Friday. So separation of variables, solving something by separation of variables. Is something where you can write the differential equation in this form. D, so let's say I'll make my, what am I going to make this? Let's make my dependent variable f and my independent variable q. Okay. And you have to be able to write it as a function, let's say g of the dependent variable times a function h of the independent variable. Okay. Then the way you solve it is get all the dependent variable stuff on one side get all the independent variable stuff on the other side, and then you can integrate. Okay, so what? Yeah, we'll talk about that on Friday. But I'm going to write this as df over g of f. And that's equal to h of q dq. And now we can integrate this with respect to f and integrate this with respect to q and get the solution. Okay, well, I won't give you any differential equation stuff to do before Friday, but we'll get into this on Friday. Okay, that's all.